Hi, so as many of you know, my name is Silvana, and my presentation will be on chapter 4.5 in our textbook, which is titled Irreducibility in Q of X. So, for some background, we'll discuss what Q of X is, the definition of irreducibility, and what makes a function irreducible. So, what is Q of X? It's the field of rational numbers. And by definition, rational numbers are numbers expressed as a fraction, a over b, where a and b are elements of the integers. For the definition of irreducibility, it is stated in theorem 4.3.2, which states, let f be a field. A non-zero polynomial p of x in f of x is said to be irreducible if its only divisors are its associates and the non-zero constant polynomial. And by associates, based on definition 4.3.1, an element A, which is part of a commutative ring with identity, is said to be an associate of an element B of R if A equals BU for some unit U. So in this case, we can see that A is irreducible because its only divisors are its associate B and some unit U. Now, what makes a function reducible? If the function has divisors that aren't just its associates and non-zero constant polynomials. So other divisors of a reducible polynomial can include other integer coefficients and other irreducible polynomials. Now, what are units? In the textbook, it's stated in definition by corollary 4.1.5, which states, let R be an integral domain and f of x an element of R of x. Then f of x is a unit in R of x if and only if f of x is a constant polynomial that is a unit in R. So to simplify, units are elements in a ring that have a multiplicative inverse. So if g is the multiplicative inverse of f of x, then f of x g of x equals 1. Now, what are the only units in z of x? It's plus or minus 1. And how do you find the inverse of an element in q of x? Well, it's simply just a reciprocal. So if an element in q of x is represented by a over b, its reciprocal will be b over a. Now, moving forward with definitions, we'll begin with 4.5.1, which states, if f of x is in g of x, then c times f of x has integer coefficients for some non-zero integer c. Now, we'll move forward with an example. So consider f of x equals x cubed plus 1/2 x squared plus 3/4 x plus 1/4. What's the least common denominator? It's 4. So we'll multiply all the terms by 4, and we end up getting 4x cubed plus 2x squared plus 3x plus 1. So now we can see that polynomials in q of x can be manipulated to be in z of x. Continuing on with our definitions, we have 4.5.2, which states there are irreducible polynomials of every degree in q of x. But how could this be proven? We can use Eisenstein's criterion, which is, I think, theorem 4.5.3. And this states that if we let f of x equal a sub n, x to the n, added up until a sub 1x plus a sub 0, be a non-constant polynomial with integer coefficients, if there is a prime p such that p divides each of a sub 0, a sub 1, up until a sub n minus 1, but p doesn't divide a sub n, and p squared doesn't divide a sub 0, then f of x is irreducible in q of x. So this means that if p divides all the term coefficients except the first one, which is a sub n, and p squared doesn't divide the last coefficient, a sub 0, then it is irreducible. So the example I have here is f of x equal equals x to the fourth plus 16x cubed plus 4x squared plus 6x plus 10 irreducible? So let's look. What prime integers divide 4, 6, 10, and 16? Since they're all even, the lowest like prime integer that divides them is 2. And frankly, that's the only integer that divides all of those. So does 2 squared, which equals 4, divide 10? No, because there's a remainder of 2. Therefore, by Eisenstein's criterion, f of x is irreducible. Moving forward, we begin with the rational roots test, which in this chapter seemed to be the most complex proof. So let us begin with theorem 4.5.1, which states, let f of x equal a sub n x to the n plus up until a sub 1 x plus a sub 0 be a polynomial with integer coefficients. If r doesn't equal 0 and the rational number r over s, which is the lowest terms, is a root of f of x, then r divides a sub 0 or s divides a sub n. But how is this so? So let us, well, since r over s is a root, let x equal r over s and s equal 1 for the equation stated above. So since it's a root, we can say f of x equals 0 equals a sub n r to the n plus a sub n minus 1 r to the n minus 1 plus up until a sub 1 r plus a sub 0. By isolating a sub 0, all the other coefficients, all the other terms become negative. And as we can see, they all have the term r in it. So we can factor out an r from all of them as shown in the third line. So we can see that a sub 0 equals r times negative a sub n r to the n minus 1 minus a sub n minus 1 r to the n minus 2 up until minus a sub 1. Therefore, by definition of divides, r divides a sub 0. So by the previous example, we know that r over s is a root, so we can plug it in. F of r over s equals 0 equals a sub n times r over n, r to the n over s to the n plus a sub n minus 1 times r to the n minus 1 over s to the n minus 1, added up until a sub 1 times r over s plus a sub 0. Now, since we want to prove that s divides a sub n, we're gonna isolate the term with a sub n in it on one side. And as you can see, all the other terms become negative. And by multiplying all the terms on both sides by s to the n, we get a sub n r to the n equals negative a sub n minus 1 times r to the n minus 1 over s to the n minus 1 times s to the n. And it's added up, it's subtracted until negative a sub 1 times r to the over s times s to the n minus a sub 0 s to the n. And by multiplying the s's and simplifying, we see that a sub n r to the n equals negative a sub n minus 1 r to the n minus 1 s up until minus a sub 1 r times s to the n minus 1 minus a sub 0 s to the n. Now, by putting it this way, we are able to factor out an s. So a sub n r to the n equals s multiplied by negative a to the a sub n minus 1 r to the n minus 1 up until minus a sub 1 r times s to the n minus 2 minus a sub 0 s to the n minus 1. Therefore, by definition of divides, s divides a sub n r to the n, meaning s divides either a to the n or r to the n. But since r over s is in lowest terms as stated in the theorem, We know that the greatest common divisor of R and S is 1. So we can assume that S divides A to the n, thus proving the theorem. Now, moving forward with roots. Roots of a polynomial in Q of X are written in the form R over S. So this is even if this is even if the polynomial is written as integers, because in that case S is 1. And there are always ways to narrow down the possibilities of roots in Q of X. So you may or may not have learned this in Algebra 2, and I kind of did. So as the example, let f of x equal 2x squared plus 3x plus 5. Now, any of our possible numerators are the factors of 5, which are plus or minus 1 or plus or minus 5. And any of the possible s's or the denominator are any of the factors of 2. So plus or minus 1 or plus or minus 2. Now, our possible roots are any combination of these integers in the form R over S. So it's going to be, our only options are plus or minus 1, plus or minus a half, plus or minus 5 halves, and plus or minus 5. These roots are confirmed or denied by plugging into f of x, and by doing so, we find that the roots in this equation are plus or minus 5 halves. So some cases are easy to factor and are easy to find the roots, but this method is helpful when polynomials are difficult to factor. However, in cases where the first and last coefficients have many divisors, there will be many more possible R's and S's to test, meaning that it'll take longer to prove whether there's a root or not. And these are only possible roots. So even though you have a plethora of possible roots, that doesn't mean that any of them are going to be roots. So moving forward with the theorems. Theorem 4.5.2 states, let f of x be a polynomial with integer coefficients. Then f of x factors as a product of polynomials of degree m and n in Q of x if and only if f of x factors as a product of polynomials of degree m and m in z of x. And this makes sense because, as seen in one of our examples before, polynomials in Q of x can easily be multiplied by the greatest common denominator of all the fractions to become polynomials in z of x. Now, theorem 4.5.4 also states, let f of x equal a sub k x to the k added up until a sub 1x plus a sub 0. Be a polynomial with integer coefficients, and let p be a positive prime that does not divide a sub k. If f of x is irreducible in z sub p of x, then f of x is irreducible in q of x. Now, we know this is true because all the elements in z or z sub p of x are included in q of x because z is a subset of q. So since all the elements in z sub p are in q, if a function is irreducible in q, then it has to be in z because all the elements in z are in q. So that is the end of my presentation. Thank you for listening, and I hope you learned something new. Thank you.